Let's. It's fine. 111. Great. So I think we're in good shape right now. I have 4 people and we're going to get started. What am I going to do? I'm going to say share the screen. If I share the screen, it's going to be 8:50 here. So we're a little bit late, kind of like we were on Friday. And we're ready to get started. So, okay, so I need to ask a question to make sure that people can hear me. I think I'm going to go with escape and then with the chat. Question in the chat. Hello?
I can hear you.
Oh, that's very good. Yeah, I don't have any thing else to verify. I can still tell my joke, maybe a little later. With this Elma coming in too. So great. If people can hear me, I'm very happy. If you need anything during the time that we have this lecture, just speak up like how I did just now, or write in the chat. I'm going to close this and I'm going to close this also, and I'm going to go to the class website. And I'm going to say that today we'd like to do the robot algorithm because we've been postponing it for so long. And then tomorrow we'd like to do superdense coding, and that's where the Mrs. State formalism ends. The one that is used in the book without any number whatsoever ends for us with that example. And then we have our guest lecture on Wednesday. Again, that is important and counts as a credit for weekly meetings. And then Thursday and Friday, we are going to look into ways in which we should extend the Mr. State formalism to be able to support teleportation first. And then the GAC game, which may not fit this week. So if I'm going into CG90, I'm going to say, for example, that if I look at the syllabus, the thing that I'd like to point out right now is the Kubica, and I'm going to go straight to the chapter on Rover, and I'm just going to essentially show you how you can look at it and do it without hesitation. So I need to model that for you. Okay, I am going to say that I have a notebook and I'm going to use it to write down. So today is July the 15th. And what I normally do is I take attendance. I have Elmar over here. And then I am also here. And then on the other side, I'm online, and so is Carla, and so is Alisa. And then Ahmad. Okay, now quickly, I don't know which Ahmad I put it. Sorry. Where is, okay, this is the participants. It's going to be Ahmad Faiz. Great. The people who are here and I'm recording and we are in good shape right now. So then very quickly, we have to get started and do this thing. So I'm going to ask some questions of Elmar because he's the only one that's here. Before I ask him, so he can tell me what he thinks, I'm going to say, how do you think this class would look if you were to be here in this room? And actually, there would be no Zoom whatsoever. Let's say there's no Zoom whatsoever. We're back in like 2015. And we're just coming to class, going to the house, stuff like that. And the answer is that you would probably have to take a midterm, that you would probably have to take a final, that you would have quizzes in class, minute papers, and so on. And then what would be the things that I would like you to learn that you could then take with you? And clearly, for each week, I would have a circuit that you would have to show you remember. One of these would be Grover, and the other one is Mani or Tiger, and the other one would be Bursty Bazirani. So we do have one thing per week that you should say, give me a pen, give me a place, leave me alone, I will write the circuit in 20 minutes or something like that. That would include the drawing, the explanation, and the calculation, which in this case so far has to be done with Mr. State's formalism. Then you say, wait a minute, we also discussed probabilities, so you could ask me for lab to do some simulations or to do some counting or to write something up for you in LaTeX inside Colab, or you could also do circuits. I can do circuits for you, and then I can also do matrices in NumPy, or I can actually get them out of the circuits and then compare them like that. So there's a lot of stuff that is both of the lab nature as well as a lecture kind of thing that you would have to do. So now, as I'm going into the global algorithm, I have to read what's on the screen, but also I have to get into my iPad because I'm going to have to I'm going to draw. So I'm going to enter my. I'm going to connect from the iPad here as well. So I'm going to go into no, not this one, how about this one, and say I want to launch the meeting, and so I will now show up on my own screen, open. It says that I have entered the room and I need to be admitted, and I was admitted just now.
Recording in progress.
Sure. A little bit of echo. Disconnect audio, and at this point, my iPad has nothing. As far as audio is concerned, I get the audio from wherever the microphone is, and we're still looking at the desktop. So I'm going to say okay for this, and I'm going to go back into my thing. I forgot what this is and when I drew it. But I'm going to go. I'm going to go in here and I'm going to share the screen briefly from share content from the iPad. So I want the screen. Start broadcast. This will take the screen, I think, from this guy. And hopefully I will soon see on my Zoom, my iPad, hopefully. It says screen broadcast. Doesn't seem to connect that way. Everything on your screen, including notifications with the report enabled, do not disturb the event unexpected notifications. I say it doesn't want to show up. I'm say stop broadcast, start broadcast again. Let's see if that works now. Okay, so I'm good. So you guys see me saying that I'm broadcasting. Yes, I want to. So finally stop the other one, which by the way, I stopped on purpose, and then I come back over here, and this is the thing that I was gonna say, that finally you get this. Let's see, when I click on this, I'm supposed to on here. How do I erase? Come on. Oh, I see this one here. So I'm going to go and say from the eraser, I'm going to use the object eraser. And this is something I've done a while ago. And now I'm erasing everything. I can make this like smaller and erase like this. And I'm going to get started. So I'm going to talk to Elmar because he's the only one in here. I'm going to, I can talk to people online as well. So 10%, I'm going to make it like, 40%. You can see in the corner. I can cut the video over here, so I don't have to worry about it. And that's basically it. So I'm going to click on this and I'm going to say this one here, but I don't want it to be yellow. Come on. Black. And I'm going to say, Elma, I have a question. You need to guide me. I do have 4 cards on the table. This is one card, this is another card, this is another card, and this is another card. We number the cards like this. So people online can vote for this too. We have to decide what we're going to do today. If the queen is here, okay, the others are not queen. And therefore they are, numbers like 2, 4, or whatever suit. And what suit the queen is on, off, it doesn't matter. This will be encoded as 3. If their rates are face down. What I would like Elma to tell me is which one of the 4 possible cases should I write the circuit for today? For example, this one, I just put it over there, is the same thing as 1, 0. I have encoded as 1-0 because if the queen had been here, again, I know the queen is there just because I put it there, but you don't. If you look at it, it's face down, so you have no idea that's where the queen is. But if you knew what I know, because I'm setting it up just like the money or tiger, this one would be the same as 0-0. Come on.
1-0-0.
This is 0-0. Okay.
I
I started 0 go all the way to 3, but then it means for me 1, 2, 3, 4. That's just the convention for me that I use at the moment. I have another possibility where I put the queen on this side. I mean on the second card, and this is going to be encoded as 0-1. So now I have only one option. The cards are such that if I knew where the queen is, I would find out that the queen is wherever it is. Now, the fourth case is going to be 1-1. Yeah. All right, so there are 4 cases, and what I would like Elmar to tell me right now, or somebody online, which case should we, I'm gonna write this down, which case should we work today? That's the question. Anybody has any opinions? So Elmar, what do you think?
have no opinions.
You have no opinions, so
No,
I
I
have
would
two
take
cards, two
zeros.
books. This is Elbow Lamb. This is the book that we said we were discussing.
Yes.
Yeah, now, do you have any opinions? Maybe now you say, oh, that's interesting, okay, I have an opinion.
This is totally off topic now, but
There are 4 things, can you choose one? Can Alisa
I
choose
know
one?
that that there are different cases in the gates. But I would just start by 0-0 because we have to do them all. in the
No, we don't have to do them one because we don't have time. So,
end.
here's what we have right now, we have Ahmad,
Yeah, I'll start updates, that's.
we have Alisa,
Or
we have Carla. Right now, people who can tell me, and then we have Elmar. Who's upset because England lost, let's face it. Elmar B. Alright, so one of these people.
it's not Elmar, it's Philip.
Did it today? Today, that's it. Alright,
Okay. Okay,
that's possible.
yeah,
So anybody that I wrote the names can tell me which case should we discuss today? You can hear Elmar, I mean, Philip, bubbling, mumbling. We do not know to what purpose. Yeah, let me just talk to Alisa. Alisa, how are you? We don't have any signal from Alisa. We don't. And Elmar doesn't know, doesn't want to talk. I think to me today, or yesterday in his spirit. What about Ahmad? Ahmad, which case should we discuss? Okay, I think Elmar said, let's do 0-0 because.
I was gonna say 0-0-2.
Okay, we have 2 votes for 0-0. And so we're going to do that case. Okay, I think Carla voted and Elmar voted. And I think that's fair enough. So I'm going to go and say. That's what it is. I don't know what it is. Can I stop sharing? I'm gonna stop sharing. That was the starting point in which we emphasize what we're looking at. And now, remember, we are doing 0-0. So we are gonna go and say share the screen because we gotta come back here a little bit. And now Control Alt Shift H. Let's just get started because otherwise we will be losing time. Yeah, so Grover search algorithm. Let's not worry too much about what's written over here. But let's read the challenges. If you have 4 cards drawn from a deck of playing cards, one of them is an ace, the other 3 are not. How many cards would you need to flip over? And so my theory is that 6 plus 3 times 18 over 4 factorial, which is 2.5, you might challenge this. It's not important to discuss that today, but clearly more than 1, right? And then we come back over here and I say that the first step in Grover's algorithm is called the initial state preparation. I emphasize that there are 4 cases and we have just agreed, like a significant percentage of the people who are able to vote right now, maybe the others are voting by mail, you know? And then the
yeah, the
ballots will come
ballots come too late.
after the class ends.
Yeah.
But they will still be counted, of course. So 0, 0, 0, 1, 1, 0, 1, 1, we chose 0, 0, okay? then you say, that's the situation, we have a space of 4 cases. Now I'm going to say, what is this circuit? And the circuit that you are looking at is in fact the circuit that recognizes 0, 0. So we will have an oracle. I said the second and the most important, the first one is state preparation. I have not shown you on this page yet anything about state preparation. But I will in a second. So now what you're looking at is the second stage, which is the oracle. Remember, the oracle is not as mysterious as you might think. I mean, if I were to play this game with, in a classical sense with Elman, if we didn't have an oracle, we wouldn't be able to know when one of us wins the game. So the situation is recognize that you have in fact drawn the queen. So this one says, I am doing that. If it is on 0, 0, so it happens that this oracle is the 0, 0 oracle that we have just chosen. I'm not sure if in the chapter we proceed calculating the very this very case, but at least we are looking at that oracle. Then what this is supposed to do is to always mark the 0, 0 with a phase and leave everything else unchanged. Now you also remember that I have discussed the control Z one day, and we emphasized the fact that now we have 2 blobs and we don't know where the Z gate is. But in that discussion, we emphasized clearly explained the fact that it doesn't matter where the Z gate is, because all the entries are going to be left exactly as they are, with the only exception of the black, which becomes, which requires 1 phase on either one of the blacks. Doesn't matter. The black blob will get a phase. You can put on the first or the second or over the entire thing or in front. It's the same thing. All the other combinations are going to be left alone. So the first step that we have to do is to make sure that we believe that this is in fact the oracle for 0, 0. The way this is described over here does not prove that it is the oracle for 0, 0. It simply says on this page that if you put 0, 0 in the input, it will mark it. But there is no information on this page that says while this is happening to 0, 0, all the others will be left untouched. So you would have to be thorough, right? You would have to say, if I feed 0, 0, it does produce a minus 0, 0. But if I feed 0, 1, 1, 0, 1, 1, it doesn't recognize that. All right, so this is where I would pull the card from the first position and I would say, there you go, that's the queen, I recognize the queen. But if I pull the card from any other position and the queen is not there, I would say, it doesn't make any difference to me. So the challenge would be to prove that this is the oracle for 0, 0 by feeding 4 possible answers in it. I mean, 4 possible situations, 0, 0, 0, 1, 1, 0, and 1, 1. Or if you want white, 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 black, black, white, black, black. And find out that when it comes out, there's only one of these combinations, which specifically is going to be white, white, that will in fact produce on the outside a phase. Now that's not very hard because the only time you're going to get a phase is if the control Z in the middle is going to be presented with black, black. You only get black, black if you start with white, white. If you get any other combination, you don't get black, black, which means that whatever you are feeding, you flip it and then you leave it untouched and then you flip it back. And so this is a very quick proof that this is in fact the oracle for 0, 0, because 0, 0 will in fact turn into 1, 1 and acquire a phase, then turn into 0, 0 and preserve the phase. Whereas if it's anything else, it's going to not move the Z gate and therefore it's just going to go back to where it was without any phase. So that's how we prove the oracle. I'm going to come back over here and say that if you're looking at this circuit, we are on a mission to actually go over all possible oracles. It's not that important for us because we decided that 0, 0 is what we want to discuss. But just briefly to understand what's in this chapter, this one here is the oracle for, and you will see 0, 1 at the bottom, but really this is the 1, 0. If we accept as the standard notation, the one that we normally use in the book and so on. So this is the oracle for 1, 0. That means Q is 1, Q0 is 1, and Q1 is 0. Reported by Kiskit like this, which is totally right. Q0 is 1, Q1 is 0. Okay, so can we have a proof? To have a proof, first of all, we feed the right state that the oracle is supposed to recognize. And if that state comes in, the barrier is where the state is being fed properly. All my circuits by default get 0, 0. If I don't want to prepare any kind of state, then I get 0, 0 by default. Then I have to put a 1 on Q0 as I promised. And then it comes in here. The only way I can acquire a phase if it's a 1 comes on this one and the 0 comes here, turn into a 1, so that the control Z acts accordingly. So if the 1 comes in at this point, it goes through unchanged, but the other one is supposed to be 0 and it has to go back to 0. The only way the phase gets produced is if the combination at the level of the Z gate is 1, 1. Okay, so that's what this is explained over here. And it says, why don't you just trace this and prove that all the other 3 leave it completely unchanged? So I don't want to do that because we already discussed the 0, 0 oracle. This is the oracle for 1, 0, or as we think it's 0, 1. That means there's a 0 on Q0 and there's a 1 on Q1. If I have that, then that's the oracle, the solution that the oracle recognizes. Meaning if on that position there is a queen and I recognize, oh, that's the queen, that's the idea. So finally I have the oracle for 1, 1, which says, all I want is a control Z. So you know that there are 4 oracles. We have chosen one, the one that we need, okay? What else? We discussed that the Grover algorithm is a circuit that's made out of 3 parts. The preparation of state, which we don't know yet exactly what that means. However, it probably involves Hadamard gates. I mean, from John's comment from a week ago when we showed Will Oliver's mathematical treatment, to now, for example, when I prepare the states by putting the right gate at the beginning, so I can start with the 0 and then get the 1s when I want to get the 1s. So this preparation of state, but I have to explain what that is. It's like this, but it probably involves Hadamard gates. I didn't show you yet. Then there is the oracle. I've shown you all 4. We are going to focus on 0, 0. And finally, there is the last part, which is called, what is it called? Diffusion, or whatever it is. So where do we emphasize, where do we provide the name for that state? Let's see, there are, I must have said this somewhere. So the second is the oracle. What's the, yeah, state preparation is the first one. Then there is an oracle, and then there's a diffusion operator. So now you know even less about the diffusion operator than you know about the preparation of state. But you do remember that there is a geometric interpretation of what the diffusion operator is doing. You can imagine this kind of like a feed-forward neural net that basically has a number of stages, and then the stages are in fact arbitrary many. I mean, not really arbitrary, many is like square root of n. And then you say, well, why not make this a recurrent neural net? That's totally fine. And so it's kind of like what we were told in the lecture, where even though the Zeno effect has a bunch of stages, we just feed the photons back into the same box. Okay, so we have strategies of thinking about this, but once again, there are 3 parts: preparation of state, the oracle, and then the diffusion operator, which is you can easily think of it as a bunch of stages. How many? Square root of n. How many? What's our n? 2. So then that's going to be in terms of whole number of iterations. Our diffusion operator has 1 step. That's why I've chosen short, simple examples for you to see that even at this level, first of all, the advantage occurs, and second, and maybe looks like ridiculously magical. And then if you say, I'd like to know what's happening, and then I don't want you to give me a matrix and I do the multiplication and I don't know exactly how, where, what happened. And instead, send through the circuit 2 white qubits, like zeros, and then see how they combine. Because in the process, you might just build the intuition of how these gates happen, produce whatever they produce, so that later you can say, I have thought up an algorithm of my own based on the things that I've learned using this Misty State formula. We don't know if this is possible because we haven't used this that much. I mean, it's being put together for the first time 7 years ago, and we're teaching it for the first time this year. But we worked on it for the last 2 years to write the papers and the booklet. So we do not know what effect or impact might have. There are other people that have used this, and they may tell us if we were to reach out and ask them, how did this go into your high school and so on. So I'm scrolling through this and I say, now I know that's the actual stages. So as I scroll through this that you've seen before, this is a complete circuit. What circuit is this? Well, the first one is the preparation of state. I'm going to very quickly move to the iPad and write down the circuit for 00 and then trace it. 2 Hanamat gates are going to be the ones responsible for preparation of state. This one here seems to be the oracle. And if this is the oracle, then it has to be 1, 1, which the text says, yes, we've chosen 1, 1. Great, no problem. And if it is 1, 1, then the rest of it is going to be the diffusion operator. So one thing that you will probably not be able to get out of today or this semester would be, how did he come up with this idea? I think that his approach was such that the math was the vehicle, and we are trying to present it in a way that is an alternative way that might just be, I guess, shedding more light to how things proceed, but probably wasn't the way he thought about it. So the motivation isn't our main goal over here, because we might not be able to get it right. But what we would like is to produce this alternative way of calculating, so you can trace what's happening in the circuit, to be convinced that you can control it, and what you say happens does indeed happen. So what do we know about this circuit, which I will write down in a second on the iPad and start tracing it. And that's the purpose of today's lecture. That there is one stage, then another stage, and then a longer stage, and we feed 0, 0. Now, the oracle that we put over here is going to have 5 gates. There will be 2 X's and then 2 more X's, and then the Z, control Z in the middle. So, okay, it's the most complex in terms of number of gates over there. But regardless of what oracle we are dealing with, we're going to do the 0, 0. The input comes as 0, 0. And if the oracle were to be about 0, 1, 1, 0, or 1, 1, it doesn't make any difference. The input will always be 0, 0. And the oracle does not generate anything. It simply says, if you are feeding me a 0, 0, which we are not going to, not even in this case where the input is 0, 0, because our 0, 0 that we have over here is the input that we put into the circuit always. And the first stage before it gets to the oracle is going to be preparation of state, which is going to prepare all the combinations in the superposition of 2 states. So prepare the state, start with 0, 0, regardless of which oracle we are using. We are using 0, 0, but it doesn't make any difference. State is prepared in superposition. We go into the oracle. Oracle does not generate anything, but can recognize. So you may say, okay, I think I understand what the purpose of the oracle is. You're feeding in kind of like all possible things in this quantum parallel way. And among all possible things, there will also be this guy. So it will mark the right one, so it doesn't generate, but it will mark it. Then the diffusion is going to say, whatever has been marked needs to be amplified and all the others suppressed. Remember that there are variations of this, as John was pointing out, where we might look, the queen could be in 2 places, then the oracle should recognize both places in some sense. And so that's a more complicated situation. Now, case just 1 place, and the oracle for that place is in the circuit. So we have 4 possible cases, there's only 1 queen, and we're dealing with 0, 0. The diffusion operator is going to be this, regardless of whether we are looking for 0, 1, 1, 0, or 1, 1, or 0, 0. So we will trace the algorithm step by step, and we start, as I said before, naturally with 0, 0. The challenge says calculate psi 2 and psi 3. And in fact, from here on, we are going to calculate psi 1, psi 2, psi 3, psi 4, psi 5, 6, and 7. And what do we hope to prove? We want to prove that if we start with 0, 0, over here, we are going to get a state that is the answer to this particular, the answer recognized by this oracle. So in the circuit that you are looking at, the answer at the end should be 1, 1, because that's what the oracle recognizes as the right answer. somehow, even though the oracle does not generate it, the answer that we are looking for gets generated through the combined operation of all three stages, preparation, oracle, and diffusion operator at the end. In our case, we are going to change the oracle over here. We feed 0, 0, and we want to see 0, 0 at the end because the oracle in the circuit is going to be the one for 0, 0. That's the one with 5 gates, 4 not gates and the control Z. So we are going to prove that that's the case by calculating the stages. If we don't have time to calculate, then I will do as much as I can, and then I will finish it at home. Particularly since what we have in the booklet is one case only, which is the case, this one that you are looking at, which is 1, 1, not 0, 0. So it would be good to do another case, especially since if we have the time, you should do all 4, right? Just for practice. This will finish our first half 3 cases of quantum advantage, where the only thing that we are dealing with is superposition. And then we will have 3 more that will be all based on entanglement. And so the first one with entanglement, superdense coding, we don't need to change the formalism. But then we have to, and then we can do arbitrary states through quantum teleportation. Okay, so I'm now going to the iPad. So you guys know where this is. Okay, so I stop on this page, and I'm going to say, I have a paper copy of this, and I will somehow refer to it while we do this. May or may not be relevant, but I'll do it. And now, that's my goal. I'm going to say, okay. If anybody has any questions, let me know. So I'm gonna go on the escape. I'm gonna say,
I have a side question. I don't know if you should ask it now.
ask it now.
Because sometimes in literature they use for the wave function this psi, but sometimes they use the phi symbol and they use both together. And what is the difference?
No difference, but I think psi is more often used. If you go to field vision, the idea is it's psi because it looks like IU, and so the field has an IU lab that does trapped ions, and he proudly shows the IU symbol and says it's the psi function. So that's the more common one. Not sure what to tell you about phi as opposed to psi.
I send you a link where I have explicit this question, but here.
But let's say, for example, if usually the unknown in an equation is an x, it sometimes could be 0 or I, and which one is the real one?
Because they do different one.
Yeah,
I
but
think.
okay, I'm gonna screen broadcast, and I think it started. There you go. I'm gonna come back over here. So we decided to do the 0, 0, okay? So because I have 0, 0, remember that we are doing this because you really should be able to operationally function within what we are discussing. So if you were here, I would ask you to do this for a quiz. Write the circuit, show me that you can do it, and it would be good for me to know that you don't know, because then we would slow things down, right? Right now I say, well, I guess you did whatever, I hope you are following, and then we move on. And what if you don't follow? I mean, I say, for example, people are watching the recordings, how do I really know? I kind of meet with them, but not everybody. And then now, if you come to the guest lecture, that counts as a discussion. I'm happy with that, but then I'm not entirely sure truly what's happening. But I'm comfortable with what's overall. But I'm just saying it would be much better for your own benefit, I guess, to participate in little quizzes or stuff like that. So I'm modeling that particular activity now. And I say, I'm going to work with 0, 0. That means that the circuit is going to look like this. First, there is a Hadamard gate. And then there is another Hadamard gate over here. This is in the stage that we call preparational state. We call this one Q0, we call this one Q1. Great. I am going to have to calculate things at this level. And I'll call them whatever I'll call them, and I have to calculate things at this level. And if we don't want to use size, let's say, I can just use 1, 2, 3. But I will use side just like in this thing, because it will sort of refer to, calculate what the thing looks like. Because that's exactly what we used to do in the booklet when I say, please print the state vector, I guess we are calling. So it's a state vector from instruction and then the oracle, and that comes out as negative vertical bar 1 0 greater than. So the next step is I have to have the oracle for 0 0, which is going to be an x followed by the control z. Here's the other x over here. And then there is another x over here and another x over here. So this is the oracle for the things that we decided to pursue and trace. Right, so I am very excited about this mixed state formalism because it allows me to trace things as if I were to do the debugging of a circuit in real life. But we know that this kind of debugging cannot be done in real life, because if you were to measure, you wouldn't get the superpositions, and you would collapse everything, and you would just ruin the whole thing. You can't possibly look at various stages and see what's happening. The moment you do, you just ruined the phenomenon. So this is the oracle, and now I have to do the diffusion operator, which is in fact of the following form. There is a Hadamard gate over here with a Hadamard gate over here. Each one of these is followed by a Z gate, right? So I think a next level kind of course should sort of provide you could look into Gene's Qiskit example that I linked 2 weeks or 3 weeks ago, and you might hear some sentences indicating why the Z shows up, why the H is there. Okay, but my goal for you would be first verify that you know how to calculate and you get what you expect, and second start worrying about how did this guy come up with this idea. And how would you be able to come up with a similar idea in this particular case? For example, do you remember? Let me explain what I'm trying to get at. So there is a puzzle that I shared with somebody in office hours. It's like this. Assume that you have two wires. But they are wicks. They burn. Okay. You don't know what length they have. All you know is that if you light one at one end and you let it burn, it will take exactly an hour to reach the other side. So if I take this is a match, and if I light it over here, it takes exactly an hour for it to burn all the way to the other end. But it burns different speeds. I don't know how fast it burns, so I really cannot say that if I cut the wick in half, it's like a shoelace of some sort. Okay, so if I cut exactly half, half will take 30 minutes, the other half will take 30 minutes. No, because it may just go super fast up until at some point, then it goes really slowly. All I know is that it takes an hour for all of it to burn. So because this takes an hour, right, and this takes an hour, you are asked to use a match box with just a way to create fire and the two things and measure 45 minutes. And so that's it. I leave you with this puzzle. You have two wires or matches, or I'm sorry, wicks, and they burn in exactly 1 hour, but they burn very irregularly, so you cannot say that half will burn in 30 minutes. And if you just know that, the question is, can you measure 45 minutes? And the answer is yes, and it's not extremely easy.
We measure the relative time difference between the two wires, and then we can use that to calculate the time difference, or like we can get an indirect rate of fire, and we measure the 45 minutes in that way.
We have Ahmad with some comment, but I didn't quite understand the comment, so I'm going to ask him for some details. First of all, let me clarify what I'm trying to do here. This is a puzzle. If I don't tell you how to do it, you may or may not solve it. Suppose you don't solve it, then it's annoying, right? Now then I tell you, because you can't solve it. Let's say you can't solve it, and you say, please tell me the answer because I can't sleep. Okay, fine. Then I tell you. The question then is, not to verify that my answer is correct, but rather to ask yourself, how could I have come up with an idea? And that's what I'm coming here to say about Grover. Let's look at the solution and see that it is the right solution. And then later, at some point, ask yourself, how could I have come up with this? How can I come up with a different version of the same thing? And so I gave you this puzzle. I have another one, but I think it's going to take us on a tangent. Let me do this. Finish the diffusion operator, which will have a Hadamard gate over here. And now ask Ahmed again for, did you want to tell me the answer to this?
Yes, Professor, I was thinking if we light the fire at the same time, and if we have a global wall clock, and if we can measure the length of the wires that have been burnt on both the sides, for a given time duration t, we can measure the relative length burnt in both the cases for A and B, for wire A and B, and we get the delta in terms of the difference in the rate of burn for both the wires.
There is no clock. The only thing that you have is the 2 wicks, and you have a way to start fire, a match.
Yeah, if we do not have a global wall clock, then I do not know how to. Yeah, I don't know that. Sorry.
Okay, but that's good because your question clarifies that you thought there might be some things. Like you can do stuff, like you can, I don't know, you have your heart is very stable, right? And you just measure how many beats while something burns, and then you say, therefore, I can try to estimate the speed. You can't do that. So there's absolutely nothing else that you can use other than use the 2 wires or wicks, whatever they are, and know the fact for a fact that they actually take exactly an hour to burn.
Can we not try to bring this into a mathematical equation? Like this is a system of 2 equations.
Perhaps, but,
Y A is 1.
yeah, but if you say make an equation and someone's like, say, let's solve it.
Well, that's what we try, right? We abstract it, then we can solve it, and then go back to the.
Yeah, so I'm not interested in a solution. However, if we were interested in a solution, I'd like to know the solution, not
We
like.
can. Yeah, I'm sorry to interrupt, but we can place the 2 wires at some angle and light the fire on both wires at the end, and we keep rotating the angle until like I don't know how to put it, but like at the time the wire 1 ends burning is where we like put the intersection. So basically, wire 1 is the x-axis, and we move the wire 2 as like at an angle with that x-axis. So in a way that both the wires like
yeah.
Oh,
are burning at the midpoint or like at the intersection, sorry, of both the wires.
yeah, I don't know what you mean by the intersection, but look, this is 1 wire. You said this is the x-axis. Where do I put the second wire?
We can place the other wire at an angle theta with this first wire,
Like this.
and the assumption is like they would be like I don't know how to do this qualitatively, but uh, out of all the points like that we can move the wire horizontally, as well as we can change the angle theta of the other wire. In that way, like one possible configuration is when both the wires burn at the same rate, so that they meet at the intersection where both the wires cross.
I honestly do not understand what you're proposing. It seems to me
Yeah,
that.
I'm sorry, I cannot formulate it very clearly. I think there might be flaws there, so yeah, I think we
Okay.
can leave the solution.
Because people, look, this demonstrates interest, therefore I'm gonna tell you how to solve the problem, and then you can tell me what you think about this, okay? So no clock, nothing, we wanna measure 45 minutes. Very quickly, take the first wire and do it like this. Yeah, I see it clearly, you didn't want to do that, so this is my wire, okay? You see, this is my wire. So my advice is, take your, whatever the name is, match, and light it here. So it's going to go like this, and it's gonna go like this. So the thing is gonna burn this way and this way. Ahmad, do you follow?
Yes, Professor.
Okay, so I would like to take 1 wire, just 1 wire, and light it at both ends at the same time. I can do it because it's a flexible wire. So now, how do you think this will go? Well, maybe they're gonna meet over here, right? They could meet anywhere, I don't care. But if they meet over here, that means that the amount of time this has burned is the same amount of time that this has burned, correct?
Yes.
Because they
Correct.
meet there and the wire is finished. Okay, this whole thing takes an hour, which means that this takes 30 minutes. And this takes 30 minutes too, correct? Yes, no? We lost
Yes.
Ahmed?
Yes,
No.
yes.
Elma is interested and agrees. So I'm gonna say that if I go back to what I had before. Please allow me to say that if I do this, I will have measured 30 minutes.
Yes.
So you say, but you said 45. I say, well, wait a minute, at least I have 30, I can do something other than an hour. Meanwhile, this other guy is right here. Let's say this therefore is the second wire, right? What can I do with the second wire? I'm thinking, if I could light the second wire here, at the same time, the first wire is burning at both ends. When these guys meet over here, maybe this guy is up to here. As I said, I have no idea how fast it goes. Let's say it goes a lot, and then it goes slowly, slowly. But what I know is that this is 30 minutes. Right?
Yeah.
Because the other one measures 30 minutes, and suddenly measuring 30 minutes is a good thing.
And now you can take the whole.
And now, since we know from the first case, like a subroutine, we can speed things up always. Then it goes as follows. Let me erase this and show you the setup entirely. Here's the wire. Oh, come on. Let me do black here, for example. Here's the other wire. Okay, that's the other one. So I burn all three at the same time. And when they meet over here, this guy is, where did you say? Something like over here. It's the same
And
thing.
now you make a loop.
And it's at the moment the first wire is over. Then this is the part that's still left of the second wire. Then briefly, I mean immediately, light it at the other end, and the remaining 30 minutes will burn in 15 minutes. That's giving you 45 minutes. Okay, so that's an interesting 30 plus 15. And you can identify a procedure of speeding things up. So what I'm trying to tell you is this is a puzzle. I have others. I already discussed this in office hours. The point here is that if you don't know how to solve it, you should ask questions, then you maybe clarify it further. Maybe you still don't know how to do it. Maybe you like thinking about it, that's no problem. Or you could say, but I want to know. Then if you hear it, you still have to ask yourself, that's fine. I thank you for the answer. It seems to be okay. Or you can ask more questions to clarify. But in the end, the question is, how could I have produced this answer? And then, is there another answer? So I'm saying that you should consider thinking about this when it comes to Grover, except our goal for Grover is to just make sure that things are checking out properly. So I'm going back to black. And I'm going to call this one stage one. What is the expression of the state at stage one? I'm going to put 0, 0, which means that as it write in the book, I say psi one over here is going to be this guy. Okay, so this is the simplest thing I'm going to have, correct? I'm going to say that the expression of the thing here is psi one. That's what the book says too, and we have 7 cases. I will describe this one over here as being psi 2, and maybe this is stage 2 if you want. Well, so what do I do with psi 2? I have a combination of a Hadamard and another Hadamard, so that's going to be write Q0 first, and then write Q1 next. And it's up to you if you want to keep it the way it is, or if you want to unravel it. And if you unravel it, it's going to be something like this. That's why I said that it looks like we're going to feed everything inside the oracle. Therefore, the actual answer will be one of those. And the oracle will be able to identify it by putting something on phase on it, such that later the diffusion operator somehow is going to amplify that one, but at the expense of all the others. So if you look into the thing that we have over here, psi 1 is super easy, psi 2 is not that hard. But what I do in the book, right, is write this down at every step in direct notation so that you constantly realize that you could have calculated the way Maria calculated on Wednesday, or the way Tommy Wong does it in his book, or the way Martina Forez is teaching us how to do it. So this is going to be the following expression. 1 over, so I can put this one over here, that sounds good. 1 over 2 times, and then what you have over here is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Not sure if you are a big fan of this notation or not. And as a matter of fact, I should have said that this guy here is really this one. And then this guy here is really this one. All right, so it's good practice, at least, even if I don't do it today anymore, but I do it once to emphasize what you see in the booklet. The booklet is doing the thing for 1, 1, we're doing it for 0, 0. But the same procedure should in fact be used. So I'm going to come back.
So what is the one for 1, 1? Is it the two dark ones?
Yeah, absolutely, yeah. So this one here is this one here, and the 0, 0 is, so that was like obvious.
Okay,
The reason I mentioned the other two is because of the order being backwards.
okay, okay.
Yeah, so now, let's say that we stay in the misty stage throughout, and just at the end, say, therefore the result is whatever it is. So this is side 2. The next stage is going to be side 3. Well, now we have a problem. This oracle is big. Therefore, I think we should go slowly. So I can't say that this is stage 3. This one here can't be stage 3. This one should be in a second. I'm gonna use red or blue. I use blue. So I'm gonna have this stage, and then finally that stage. So instead of 3, it's gonna be 5. This is stage 3. This is stage 4, and this one is stage 5. So I'm gonna have individual stages in the oracle too, because I just wanna look at this in really, really slow motion. I will then call this one side 3. I'll call this one side 4. I'll call this one side 5. And instead of 7, I'll probably have 9. 6, 7, 8, and then at the end I have 9. So that's what the book says. The booklet actually goes over all the cases and calculates everything. And it says, therefore, you've seen what happens if you choose the situation where the queen is in position 1, 1, which is the 4th position. But the other 3 should be done the same. And there's like the homework, because it's like more than a challenge. It says, work out the other 3. What we are doing right now, because we chose 0, 0, is to work one of the other. So this one here is going to be size 6. This will be size 7, and this will be size 8. Finally, the last one is size 9. All right, so I'm going to go and write size 3. What am I looking at size 3? I have 2 options. Size 3 is going to be x applied to this guy, and then x applied to this guy. Or I can just consider x being applied to each one of these in this superposition. So I'm going to say the following. I'm quite happy with how things proceed so far. I'm going to cut this here, go back to black. And I'm going to say I could think of side 2 as being a combination of 2 wave functions, one for Q0, one for Q1. So I could say that psi 3 is in fact equal to x applied to this, which is the output of the first Hadamard, and then x applied to this guy. But they are the same, right? And this doesn't come as any surprise, and you've seen this before, that x applied to a superposition is going to produce the same superposition with the order reversed, but the order is irrelevant, so it's the same thing. So we are going to come back here, and I'm going to say that this is going to be x applied to white, which is black, and x applied to black, which is white, and then this one is going to be the same thing. And I have commas in between them. So now that I've transform those superpositions because X applied on them, I have to really acknowledge the fact that what's coming out of it is the same thing. So look at black, black. And then I have white, black. And then I have black, white, and then white, white. So it's the same thing that I had before, just the order reversed. Meaning I should really say that psi 3 is the same exact same thing as psi 2. Like this. It's exactly the same thing. Now I apply Control Z. So psi 4 says you are going to take a Control Z and apply it like I don't know, Control Z. Maybe we can mark it like this. I can't use Control Z with an arrow on top because the arrow has to go right or left. I know it doesn't make any difference, therefore I don't want to draw it. So I'm going to say Control Z applied to this superposition. Either way you want to write, I could just write it this way, the way it came out. I'm going to write 4 possible combinations of 2 qubits. The first one is black, black. The next one has a black here. The next one has a black here. And the last one is a white, white. So now what's Control Z going to do? It's going to take the black, black and put a phase on it. I can put a phase in front on one of these 2 or over the whole thing. And then all the others are going to stay untouched. So psi 4 is being calculated. I guess I'm going to say 3 and 4. We did this, we did this, we did this, and this. Now we're moving to psi 5. So when I'm moving to psi 5, I want to apply the x's on those. I'm going to do it as follows. Look at psi 5. It's going to be this will be the argument. And I'm going to put a control knot on the first one and control knot on the second one. So all the pairs that I have are going to be changed accordingly. So I could possibly maybe do this by trying to split it into 2 superpositions and then apply X on each superposition. Or I could just say that this will automatically be each qubit is affected by the X. So I'm going to say if you look at page 45, the notation that I have over there is going to be something like this. X of black, X of black. In other words, you apply the 1 qubit gates to the individual things. That's the first thing, this one. This one here is this when you apply an X on each one of them. And then you go back to this and you say, I'm going to say X of white, X of black. Then you have X of black, followed by X of white. Then you have X of white, followed by X of white. This is what's happening if psi 4 is basically the input to 1 qubit gates of type NOT. And that means that X is going to work, each one of them will work on their own qubit. And what you get over here is going to be white, white with the face on top. Then here you're going to say this one is black and this one is white. The other one is going to be white with the black. So this one here is this one here, this one here is this one here. And then you say I have the last one, which is going to be 2 blacks. I have 2 black blobs, and that's psi 5. So now I'm going to come back here and I'm going to say I'm going to erase some of these things. I'm going to go to object eraser. Assume that I calculated everything correctly. Then I'm going to carry psi 5 at the very top and then keep calculating psi 6, 7, 8, and 9. We may or may not be able to finish, but we're going to get really close. So we know the answer. Start with 0, 0 because we start with 0, 0 always. And here, because the oracle inside is a 0, 0, We just have to get 0, 0 at the end. So I'm gonna move psi 5 at the very top, and I'm gonna say, I just calculated psi 5. This is psi 5 is as follows. It's going to be white, white with a face on top, and then black, white, and then white, black, followed by black, black. Good, that's psi 5. Now I'm supposed to keep erasing this thing. To get into the next one. I would like to calculate 6, 7, 8, and 9. So my next step is psi 6. I just told you what the procedure would be. I have a pair of qubits, and I'm feeding them. I have a pair of qubits, and because of the superposition, I have a superposition of pairs, and I'm feeding this pairs into two Hadamard gates. So this is what's coming on Q0, and this is what's coming on Q1. Those are two wires. Good. I'm going to come back over here. I'm going to say that psi 6 says, please apply H to white, and then next to it, H to white. Come on. I'm going to move this to the right and say, yeah, but now I need this thing. So I have moved it to the right. So I have H white for the first one with a phase on top. That's the first pair of qubits. Each one of them is affected by a Hadamard. And then I'm going to have H of black, H of white, then H of white, H of black. And finally I have H of black, H of black. This is a simple circuit, and as I said before, we can't afford to do more complicated ones. But at this point, you can tell that the calculation gets a little bit overwhelming. Now, because it's 9:50, if it takes me 10 minutes to finish psi 6, that wouldn't be bad, because I'd like to, because we are now really on page 45, where we are calculating a phase, a wave function that really takes a while to calculate. And your goal is to calculate slowly but correctly rather than super fast. So I will dedicate myself to this psi 6, and then I'm going to switch to the booklet to show you the equivalent calculation that happens on that page, so you know what it is. After psi 6, then there will be 3 more stages that maybe I'll do later tonight and post them separately. So okay, what happens? 244. See, anyway. I don't want this. So now I'm going to say is equal to. Okay, what is that equal to? I'm just trying to
face it's
yeah, so we're going to go slowly.
Face and the black and the white and the black.
Yeah, so I'm going to say I have a superposition of white and black. That's what the first H does, combined with a superposition of white and black. Small situation, small circuit, but this will kind of explode a little bit, not too much, but it will explode to some extent, and you have to calculate carefully. That's what that term is. This term here is going to be white, black with a phase, and then it's going to be white, black in the second one. Okay, now this term that I have right above, so I'm talking about this term now, right now. They don't want you to think that maybe that's a phase or anything, so come on. Let's take that out, and I'm going to put this back to where it was, and I'm going to say this is white, black, followed by white, black with a phase. That's what H of black does. Finally, the last combination, so we had 4, right? But now we have, for every 4, we have 4, so there will be 16 terms, and that's the extent of our explosion. We're gonna go and say, this is white and then black with a phase, followed by white and black with a phase. You understand what's gonna happen right now. When I open these parentheses, I'm going to get actual combinations of pairs of qubits, and the phase is going to be such that some will cancel, some will not. And I'm ready for that. What happens when I put a phase on a superposition? everything inside is going to change, correct? So I'm going to say that this here is white, black. That's okay. It's going to be black, white, and then black, black. And there's a phase on top, right? Followed by white, white, and I open the parenthesis now. Black with white, then I have white, black, and then I have black, black with a face on, say, this one. And then I've just done the second one. I have to do the next one, which is going to be white, white, black, white, and you have to be careful. Then you get white, so white, white, black, white, white, black with a face, and then black, black with a face. Finally, I have white, white, and then black with a face, white, and then I have white, sorry, black with a face. So white, white, black with a face, white. Hang on. White, black with a face. Now go back. So I have white, white, black with a face with white. Then I have white, black with a face. And then black with a face, black with a face. So now I'm going to start saying, how do I deal with this? All of them are supposed to get a face. So if I have a bunch of outcomes and the entire superposition get a minus, every single outcome is going to participate as such. With every single outcome is going to change face. So it's going to be like this. White, white with a face. White, black with a face. Black, white with a face. And then black, black with a face. The face is for both, right? Then I have white, white, and then I make this one to be, I put a face on top of it so that I just think of it as if it's a minus in front of it. Then I have white, black. Then I have black, black. I copy what I have on top because I'm going to start canceling them. White, white is over here. I have white, I'm sorry, black, white. Then I have white, black with the face on top. Then I have white, black again with the face. And then I have white, white. Then I have black with white and right underneath. White with black, black with white and so on. And now this one is going to be black, black because the two minuses disappear. So I'm going to use a color to say, I'm going to use red to cancel things out. So let me start canceling, for example. Look at this guy, which is white, black with a face, and this one, white, black, they're gone, right? They are the same thing, but they have different face, so they destructively interfere with each other. Look at this white, white, and look at this white, white with a face. They are also gone. So next I'm going to say, look at this black, black that has a face, and the black, black at the end that have no face. So they cancel each other. And this is like the effect of us inside the diffusion stage, which is just entered, where things are emphasizing some solutions and then are suppressing the others. So what else can I tell you? I have white. Let me do blue now. If there isn't, I still have to look at terms that I identify. But if I can cancel them, then I'm just going to just group them somehow. So let's see if I see a black, white anywhere with a minus. So look, this one is black, white with a face on top. Great, they're the same, right? Let me see if I have a, and so I'm going to change the color now to red, for example. What about white, black with a face? There's white, black with a face, okay? Hey, I have a white, black with a face here too, okay? So I say there are 3 of those, I guess. But surprise, surprise, if I go to black, to blue again, see, where am I? This one here, you can see a little bit dot over here as I'm just about to, I'm hovering about. So black, white with a face, I have 2 of them, but there's also one here. So there are 3 of those. Okay, next, I have the following. I'm gonna go back to red. And I'm gonna say, hey, let me bring up, as I'm trying to match these things over here. What am I trying to build up? Well, I'm just gonna say, I don't want to erase anything. I want to get green, for example. So we are now unfortunately exactly at 10. We're now starting to clean this up. So I say, there's a white over here. Okay, nice. Is there any white anywhere else? Yeah, there's a white over here. Okay, what about the others? I see black, this one. I see a black, this guy, with a white, see? But look at this side, that's the same one over here. So I'm gonna cross them. And now I only have 2 of those. And now I'm looking to see if I have stuff that I haven't considered. Here's a black over here. That I still have, this one here. And I don't see anything else that I could group with it. So if I wanted to write this down, I would just put it together and just keep it like that. And of course, the danger would be that I have skipped something and I copied something incorrectly. So then, let's see, okay. So then I'm gonna have to say equals and continue the calculation and make sure that I simplify it. Okay, so at least at this point, I'm going to stop the sharing. At this point, you understand what the setup is, how many stages we have. We started something we haven't done before, and we got to size 6 and we have to stop. So I'm going to do the following now. I'm going to go to Zoom and say stop share, because I'd like for you to know where we are in the booklet. And for all of us to just try to finish this at home, and I will post what that looks like, because I don't have it in Kubica, right? So I want to do it in the Kubica. So as I come back over here, I am going to say Control-Shift-H, and this is where we work. If you understand that this is a thing, except we have a different Oracle, as you scroll down, these are the calculations that we did up to the point where the most sophisticated one comes into play. And as I said, this is intimidating, but if you're careful, then you come up with something out of it, okay? And in the video, we have exactly what I did. So if there's a mistake, I will catch it when I'm gonna work it out again. So I'm gonna follow the exact same steps, but for the Oracle that we have chosen. And we were in this stage at this point. What else is left? Not much. Okay, except at the very end, even though everything cancels properly, the way that calculation is going to proceed, it might explode again in 16 turns. And when is this explosion going to occur? Whenever we use Hadamard gates. And as you can see over here, there will be 2 stages. It doesn't matter how big or complex the Oracle is. This one is with Hadamard gates is in the beginning, so that's very easy. But there will be a big moment after the first pair of, the second pair of Hadamard gates, and at the end. At the end, it will explode, cancel very, very nicely to a very good answer. Here, it's going to explode to 16 terms, and then it will cancel most of them. And this is really where we stop. We have to go into the Z's, and then we have to go into Control Z, and then the Hadamard. So I've done half, I'd say. So now you know how to do it. I will finish it and post it as a slide, and then we can talk if anybody has any questions tomorrow. We also have to discuss superdense coding. I'm going to give you for superdense coding 2 references, one to the Qiskit textbook, perhaps an older version of Qiskit textbook, and then the other one will be John Watrous from IBM Quantum Education. And we're just going to discuss superdense coding as well. Why is it the quantum advantage situation? What are the things that we are looking? How can we apply the Mrs. State formalism? Why is it contradictory or paradoxical? And and then just finish. So this is not as involved as the super dense coating is not going to be as involved as this one. It will, however, rely on entanglement. So at some point you will notice that this one doesn't have any entanglement, just superposition. That's basically the lecture for today. And I'm glad that at least we did half of Grover. And if you had the time and the inclination, you could try to finish it and either find if I made a mistake or just finalize, get to the end with the right answer. So that's all. Any questions before we stop recording and disconnect? We also have Jack. So let me write that Jack is also here. So Jack, I don't know when you joined, but the basic idea was we discussed Grover and we proceeded with a choice that wasn't in the booklet already, and we did almost half, maybe a little bit more than half. And I'm going to post the recording and then finish it and post it as a slide later today. Okay, if there are no questions, then thank you so much for your patience and comments and feedback. And I'm going to stop recording and then I'm going to disconnect. And I will post the remaining derivation later today. Escape. I hope everybody has a good day today. Thank you as well. So now I'm going to go escape again. I say stop sharing and I'm going to go.
It was not here.
Where was not here?